Now, if we start to include air resistance in our reasoning, then we all know that that will affect the motion of a falling object. So we're going to look at that in a bit more precisely detail. And looking at a parachutist, now parachutist actually has two aspects to their motion. So they've got them falling without their parachute open and then falling with their parachute open. So we're going to use this simulation to look at it. We'll probably need to go through it a few times. So if we start by watching, when I click this to start, watch over this area to the left here, and it shows you the forces. And basically, as soon as the parachutist leaves the balloon, then we know that their weight is pulling them down. But we know that that's going to make them go faster. And we know that air resistance, in common with frictional forces, increases as you go faster. So if you watch the force arrows here, you see the weight is fixed, but the air resistance is increasing. And eventually it balances the weight. And during that point, then you get constant velocity. So we'll just go back and watch that once more, and then we'll concentrate on opening the parachute in a wee second. So the weight arrow is fixed, the air resistance increases, then it gets balanced, and at balanced forces you get constant velocity. So you get that wee bit of time there where the velocity is constant before they've opened the parachute. So that idea is known as terminal velocity, that if you drop an object, it won't keep accelerating forever if there's air resistance. And it will reach a point where the air resistance balances the weight, and that will be what's called its terminal velocity. Balanced forces means constant velocity, so it's not going to get any faster. And basically the terminal velocity for different shapes of objects or different masses of objects are all different. So that's why we know something like a ball will fall quicker than a sheet of paper. Now into the mix, if we throw in the idea of what happens once you open the parachute, well, the parachute drastically increases the surface area when it's already moving quite fast. So at that point, you get a sudden increase in the air resistance. Now, it's not going to make the parachutist move upwards, because remember, it's already moving downwards at quite high speed. But what it is going to do is to slow down its downward velocity. So you have an upwards force while you're moving with a downward velocity, and so you get this point in the graph where you dramatically slow down. But as you slow down, the air resistance is going to decrease until once again it balances the weight. So with the parachute closed, we had the balance forces. The parachute open, we have balance forces again. But the key idea is now that with the increased surface area, you have balance forces at a much smaller speed. So the terminal velocity with the parachute open is much smaller, and therefore you fall more slowly and more safely, so that when you land, you're not going so fast that you injure yourself. So that's the concept of terminal velocity. In actual fact here we've looked at two terminal velocities. Terminal velocity with the parachute open, this first section here, and the second flat section, terminal velocity with the parachute closed. We can also look at terminal velocity in other situations, not just falling objects, but for instance a car has a terminal or maximum speed. And basically what's happening here is the engine force, if you make the car accelerate, let's assume it's just staying constant, you've put the foot to the floor as the phrase goes. But as the car gets faster, the air resistance increases until once again it balances the engine force pushing the car forward. And at that point the car can't get any faster. The forces are balanced, it will have a constant velocity. And that's what controls the maximum velocity of a car. And this is all assuming perfectly flat road. So basically if you want a car to go faster, two main things you can work on. You need a more powerful engine, so you get a larger engine force, or you need to improve the aerodynamics so you can reduce the air resistance at a particular speed. But eventually the air resistance and the engine force will balance and the car will reach its terminal velocity. If I stop the engine force, then the air resistance is going to slow the car down, and that's a terminal velocity. Okay, so the velocity of the car increases, the air resistance increases, it acts in the opposite direction, and it's large enough so that it's equal and opposite direction to the force the engine provides. So the forces are balanced and the car no longer accelerates, and that's its terminal velocity there.